Yeah, thanks so much for inviting me to the workshop. And I want to share some thoughts about the current state of ASR and what are still open research problems. So it's very exciting to be in the ASR area in this exciting time. So we got historic results by many companies actually to achieve very low order rates across multiple tasks. So Microsoft had it for switchboard. Baidu with their Deep Speech 2 had amazing results with phones and over phone, and they showed that it's faster and more accurate than typing on the phone to speak to the phone. IBM and Google has systems very similar, and even the unpublished commercial systems are reaching the same quality. But what we are actually missing is the meaning of language. And I'm really happy that this is also showing up in the media, because what we are thinking about as speech recognition as researchers is very different from what the mainstream people might think about. People think about conversational intelligence. And I'll come back to this problem at the very end. I would like to thank Keith for his talk, because I'm returning back to exactly the same points that he was talking about. So I will fast forward very quickly to the current state of the art. Then I will highlight two research papers that we did that are very aligned with the topic of the workshop. One of them is to understand why LSTM acoustic models are better than DNNs. And the other one is to augment LSTMs to be more robust to unmatched test conditions. Then I will set a couple of open research problems that are very related to what we just listened to in Keith's talk. So, of course, the current advance in ASR is not due to one area. So it was like huge advancement in acoustic modeling, parallel ones in language modeling, huge advancement on deep learning and toolkits for fast prototyping, and of course, chip storage allowed us to have tons and tons of data, and GPUs allowed us to have tons of computation, not only for single GPU, but also techniques to parallel train over multiple GPUs. This talk will only focus on some of the work that happened along the acoustic modeling direction. So I will start by the first step, moving from GMMs to DNNs. Again, this is the second appearance of DNNs for speech recognition. Of course, there are many reasons that we can think about why this is the case. One of them is multiple layers of representations allowed us to, for example, normalize for unwanted effects. If we are using the right representation at the input, we can marginalize out unwanted effects. And this is, I'm referring here to one of the experiments that we did by looking at, for timid, when we examined learned representation across multiple speakers saying the same utterance, we found that when neural networks are fed with the proper features, at the time it was male frequency spectral coefficients, they are capable of marginalizing out speaker effects and focus only on the content, implicitly without any explicit force in the objective function. So this is something that we found, and then we injected later on in CNNs. And by the way, I'm not talking about CNNs in this talk, just to keep the talk coherent and focus more on recurrent models. So the point of having multiple layers of representation was very important. Also, the use of very large number of output classes was super crucial, very important to achieve these very good results. And this is a bit different from what was used in the first appearance of neural networks back in the 1990s. And then, of course, the data that we have now. So I was actually thinking about the 4 reasons why neural networks were not working in the 1990s. Yes, Yeshua.
Actually, from 1990, when I was doing this, you're only doing the 60 classes or something. But Bullard, a little bit later, had the tripods. So that was the early 90s.
Exactly. But this was not the mainstream. And this is the problem.
True.
So it was like very little experiments. Actually, they had a golden opportunity at the time, but to be honest, they didn't have that amount of data or that amount of computation. But there was like, actually all the ingredients were there and all the ideas were there. And there was like many experiments that showed that yes, this would be the case. But of course, because GMMs were like working like crazy, and again, because of like funding is like pushing for this 1 extra % of improvement, it's always kill innovation in this area and just focus on engineering efforts to get GMMs better and better. To be fair with the first appearance of neural network, actually, it was like almost everything, all the ingredients were there. And by 2012, it was apparent in the industry that DNNs is the way to go by like work at IBM, Microsoft, Google, and us in Toronto, and many other academic labs as well, and industrial labs. Then, again, like I'm skipping CNNs here because I'm focusing on recurrent models. One, like from GMMs to DNNs, this was like about like 25 to 30% relative improvement on word error rate. Then the second or another move that are very important is going from DNNs that takes spectral windows as input and go to recurrent systems for LSTMs. Again, this is the second appearance. Alex Gibbs used LSTMs in his PhD for TEMET before. But then when he came to Toronto as a postdoc, we started chatting together, and he was like super excited of like with the recent result we got for speech, and we wanted to apply it for TEMET again. In this version, we, of course, like one difference from DNNs that now, rather than looking at the window, we are looking at the entire utterance. We are going to think about like, is it like a reason why it's working well or not? In the next slide. But
before you go,
sure.
I apologize. The acronym means?
Yes. So this is very important. So when I'm talking about LSTMs here, I'm talking about a general class of neural networks that are recurrent. So that consume like 1 frame at a time, and for probability of certain class at some point, it look at the entire history. So one particular type of recurrent networks is a long short-term memory network that not just look at the entire history, but also augment the neural network with an explicit memory in it, so that it allow memorization of what happened over long periods of time. And like Yesh also worked like extensively back in the 90s on recurrent models. And actually, like LSTM, the interesting things, I'm not bringing anything new today. Like all of them are second appearances. All of them are models that has been developed in the first appearance, the 1990s. But we are just like bringing them back and putting them into context and how to get them to work well. So in this work, we use recurrent networks for acoustic model and also for language modeling. We use the CTC objective function to optimize for the correct sequence, not just the phone at the current middle frame. We got good results for TEMET and Wall Street Journal. It was like really exciting when we did that. But to be honest, the actual great result got when Google used the same techniques and add more to it. And through tons and tons of data and tons of computation, and did it on a large scale. So this is where like it was super clear that LSTMs does work. And they also used CTC. We can argue like if CTCs are like, CTC is like, return back to the acronym, it's a very weird acronym. Like you can think of it as like MMI. Like it's more like a sequence objective function. So yeah, so returning back to the paper by Google, I'm just referring to one paper. They have like a list of papers that are actually acting like using LSTMs and CTCs in different setups with different flavors, but this was the first one of them. And the question that I was thinking about is why exactly LSTMs are better than DNNs? Because in one of our papers, like I was like removing one thing at a time. It's like, okay, it still works, still works, still works. Like what exactly happening? Why LSTMs are working? So in our timid paper here, we had like a gigantic system that has like many components. And I was thinking like, where is exactly its gain is coming from? I was like removing one block at a time and see where is the gain is coming from. And then I found that it's only the LSTM that is the most important thing. But why is the LSTM cells or like utilizing a recurrent system is important? Is it because it looks at the entire utterance? So in case of unidirectional LSTM, I'm conditioning the current prediction on the entire history. In case of bidirectional, I'm conditioning the prediction on the entire utterance. Is it the reason? Maybe. This is the reason because it can learn some global structure over input sentences. So implicitly, I'm learning some representation that is not defined by researchers, but these representations are learned from the task. Maybe some sort of like implicit language model. Maybe it marginalizes out unwanted global information related to the session, to the environment in the utterance. Another possibility is it's not because we're looking at the entire utterance, but actually because it's recurrent, because it takes the past, merge it with the future, with the present, to generate the future. Like it's more like this kind of integration over time that's really is helping us here. It's some sort of like a fine-grained modeling of the evolution of features over time. Maybe this is the reason why LSTMs are working better than DNNs. So in this work, in this paper that we published in December 2015, there are like lots of details in the paper about how to make the system scale, train them on many GPUs and how to fit them in memory. There are lots of details. I'm here just like talking about the higher order bits of this paper. So what we did is let's constrain LSTMs to focus only on a window of speech, the same window that we used to use with DNNs. So for DNNs, we use about like say 30 millisecond window to predict the middle frame. I'll do the same thing for LSTMs. Engineers might think about that as just like resetting the hidden state every 30 milliseconds. So within a window, I'm running a bidirectional LSTM to predict the probability of the middle frame, exactly as what we were doing with DNNs. The interesting thing was that regardless of how narrow this window is, the LSTM is consistently better than DNNs. So it's not the matter of learning global thing. It's all about capturing local information in a better way than DNNs were doing. So for the best performing systems, we train, yeah, go ahead.
How local is local?
So local here, I'm like when I tested that, I was playing with like, for example, for Temet, I was going to like 7 frames, or frames are like at 10 milliseconds shifts to 30 frames, which is like 300 milliseconds. And then the best systems was like for DNNs, I was like increasing it to say 30. Beyond that, it was degrading. LSTMs was improving even like around like 45 or 50 frames. So about half a second. So, but the phenomena or like the same observation we had was going on and on, even for a very small window sizes.
DNN, like what are we talking about?
I'm talking about feed-forward, like vanilla feed-forward neural networks.
So like fully connected, not
Fully
convolutional.
connected, no convolution. Yeah, I'm skipping. I mentioned I'm skipping convolution for the talk today because I'm just like focusing here and the next couple of slides on recurrent models. So just like basic DNNs. There is like, I'm sorry, go ahead.
This is acoustic modeling with CTC. So the task is
No CTCs here. It's just like, again, like CTC is something that now there is like lots of argument, like is it helping or not? And now there is some consensus that it's helping for some practical reasons, but not necessarily to learn a better representation. I'm talking about like the engineering empirical results here. So, and these are like coming out for like many, and I think like Brian can say more about that. I think like there are like many recent papers coming about like arguing like is CTC is better or not, like how do they compare, do they improve if like upon sequence training or not. So this is like a big argument, but the kind of the bottom line is that LSTMs are really, really important. Then the other components we can argue about them. So in this system, everything is like here what I'm talking about in this paper, it's cross-entropy training over spectral windows, no CTC training, and no, these numbers, there is no discriminative training happening afterwards. So when I say discriminative training, in production setups, people use lattices to generate some competing hypotheses using language models, and then fine-tune the acoustic model to be sure that the correct hypothesis is better than all the competing ones. Yes.
Here you're just using some aligned phonetic sequence and frame-by-frame phonetic targets.
Exactly like what we were doing with feed-forward neural networks. Yes, exactly. So this was the main point, is that let's bring them back to exactly the symbol model and see which one is better, like DNNs, like feed-forward. Again, like I would like each model was fine-tuned to the best performance. DNNs and LSTMs, bidirectional LSTMs. The reason to do this experiment was, let's suppose that tomorrow we have an idea on how to squeeze more information out of the spectral window that's not recurrent. Do we really need recurrence or not? I think the take-home message from this work is that it might be not. Relying on a window might be good enough if we have a good way to squeeze this information from that spectral window.
so how is it when you introduce noise, for example?
This is the next slide. So this is a very important question. So just to wrap up with this.
The LSTM is only to do a good job of extracting information in a single window.
In a very local window, exactly.
Really require the long-term aspect.
Exactly. And this is the interesting thing that I found by doing this work. I was super excited just to understand why they are working so good. Is it because of a global thing or just better modeling on the local neighborhood?
So same information is processed differently.
Exactly. And dramatic difference in order rates.
So in my thesis in 1991, I was comparing recurrent nets, not the LSTMs, but the vanilla ones, to convolutional and feed-forward. And they were already doing better, but I didn't do your experiment.
Yeah, so at the time we didn't have enough computation just to do all the experiments that we would dream of. But now, you know, of course, like doing it in a recurrent way is good for production reasons, like you know, for decoding time, etc. Like keeping the state is always good. But this experiment was good just to show why LSTMs are better, and we found that because it's better in extracting this local information. Yes.
So should I understand this as the LSTM is better because it's encoding the frame relative to the surrounding speech as opposed to just as it's sort of
As a feed forward, as a template, exactly. It's a difference between memorizing a fact and understanding it. You know, if I understand the fact, I can express it, I can distinguish it under noisy conditions, you know? But if I'm memorizing something, if it has a tiny change, I might not recognize it. Yes?
Now, some of the attributes of the recurrent nets here are shared with the convolutional nets in the sense that you have shared across time.
Exactly.
So it'd be nice to know where they fit in this experiment.
Yep, coming. So there is some experiment, but this is very, very good point, because what I'm thinking about that recurrent systems are just fine-grained convolutional system. It's a learned convolution that I don't do pooling with fixed kernel size, I don't do convolution with fixed kernel size. I'm learning everything on the fly. And this is the beauty of recurrent systems. Yes?
So just to make things clear, these recurrent models, to get efficient training on GPUs, what one normally does is takes some set of utterances, segments them up into roughly 200 millisecond chunks, takes a set of those, does training on the GPU, and then you just iterate in that way. And this gives excellent performance, and then we've done the experiment where we try widening the chunks that we do the training on to something like 400 milliseconds, and there's absolutely no impact on performance. So the operation of these recurrent models is definitely local.
So this is a very, like, at least this is the states now. Maybe they are local because we don't have better optimizers. Maybe if we have a better optimizer, it will memorize more information, and then we will gain that. But I'm talking about here, there is no proof about anything, just the empirical result with the current status of optimizer.
Better long-term memory, because LSTMs aren't perfect in that respect.
Exactly. This is one point. Yes.
So I just want to know, is it possible to determine whether that DNN with some parameter setting could do the same computation as that LSTM? Because you have to distinguish whether, is this a learning problem or is it a computational problem?
Very good question. And I can tell the same question is DNNs and CNNs or like I can tweak DNNs to be convolutional somehow. There is a paper that we did at ICML 2016 that just talking about that thing. What's the difference between shallow and deep networks? You can again tell the same thing. Shallow networks and deep networks. Can be the same thing if we have a better optimizer? Convolutions versus deep nets. It's a paper that, yes, we call it extended data Jacobian matrix. It's a kind of a funny name for it because of the way that we were using to analyze neural nets. And what we found is it's super difficult. It's almost impossible for DNNs to be as good as convolutions, let alone the extreme case of convolution, which is recurrent.
Compute, is it a problem in optimization, or is it that the LSTM provides some implicit prior distribution over things that can be learned that helps, reduce the parameter search?
I think what is happening is the ability of the network to kind of be resilient to transformations. So in case of LSTMs, you have this infinite capacity to dynamically adapt to stretches and compression of spectral, like time frequency patterns. To do that with a DNN, again, thinking templates. DNN is all about templates, finding this template in the input. You need to have exponentially many number of templates to match this performance. So in principle, yeah, like theoretically, yes, if you go to the limit, but practically, even with a very good optimizer, given that you're not going to infinity, it's very difficult for DNNs to do that. And I will, of course, it's still an open question. Again, all these, it's very empirical results. There is no proof about it. So definitely, it might be completely wrong. But with the current state of knowledge and current set of technology that we have at the moment, this is the observation that's coming over and over again. And one very last comment that I want to mention for this work is that I'm taking this number actually from another paper that our friends in MSR did to say the same thing that Brian mentioned. which is if I'm working with like a limited window, we get, again, no sequence training, no CTC, again, still the basic cross entropy training for on switchboard. In this case, we're training on 4,000 hours of speech data, about like we're talking a billion data points. We get 10.5. If we train a full sequence LSTM, we get 10.3. So it's a very tiny difference if there is any. Yes.
I was wondering if you could clarify why you say LSTMs are all about templates.
Oh, no, DNNs.
Oh, DNNs.
No, yeah, I think like when I'm thinking about DNNs and LSTMs, I'm thinking about DNNs more like looking for a template, while LSTMs is about like one's more like memorizing facts, and the other one understanding the fact. To understand how frames are relating to each other, like how the pattern is evolving over time and frequency. And this understanding is more like the smart student and the kind of like student that is just memorizing the facts. And this is, I think, this is the difference between LSTMs and DNNs.
Now, 1,000 hours of data.
Yes.
No, but I understand from Brian that 200 milliseconds is enough. You don't need to do more for the local, acoustic mode, for local frame acoustic mode.
Yes, yes.
So why do you need 4,000 hours?
Oh, 4,000 is the data set size.
Yeah,
Is the
but
entire.
why do you need that big of a database if you talk about local frames and you say 200 milliseconds is enough anyhow?
So
Because there are many possible variations of the 200 milliseconds
Well,
frame that
but
exist, and you
you
need a lot of
need
data to capture
4,000,
that.
but I don't know if you need without noise. We talk in speech. I don't understand why you need 4,000 hours.
this is not, I would say this is clean speech. This is telephone speech. This is like telephone speech. Like actually, it's like 2,000 of 16 kilohertz. Another 2,000 is like 8 kilohertz. But one thing that we found with all sorts of neural nets is that like throwing more, allowing us to discover yet to be discovered features. Like maybe with a tiny, and actually this is something that you're like right with that regard that DNNs are capable of generalizing from a very, very small amount of data. And this also we have seen that even with a very small amount of data, even normal DNNs, and this ability is like even more for LSTMs, it can generalize from a very small amount of data. But I believe we're still missing something. We still need to understand more about these models. That as we throw more and more data and increase the capacity of the model, still we're improving. Sometimes it will plateau in the future, but still we haven't seen that. We didn't hit this limit yet. So
You were about to move on. I would ask another question.
sure.
Is it the magic in the LSTM or in the RNN? Did you compare with vanilla RNN or?
All this work we're doing with LSTMs. And vanilla RNNs, a bunch of experiments. And not only me, lots of other researchers and labs. Yusho is the expert in this area. He actually was one of the guys who was breaching RNNs back in the 1990s. And lots of us was kind of like suffering by vanishing gradients in RNNs.
To get vanishing gradient issues?
Yes, I did some experiments that to compare the kind of to see the effect of vanishing gradient. I found that for RNNs, they tend to forget what's happening within 9 time steps in the past, while LSTMs are memorizing about 40 time steps in the past. And this is why I guess RNNs are working amazing for language models, because for language model, the kind of history that you carry is about like 5 to 6 time steps in the past. And this is why RNNs are very good. Like you don't see gains by doing LSTMs for language. But for speech, 5 time steps in the past is like nothing. So this is why RNNs are not flying here. You need to have longer context. So the next snapshot, I'll try to go quickly with that, is how can we augment LSTMs to be even more impressive? So in this work, again, the second appearance, nothing new, is to use time frequency LSTMs, to use LSTMs over 2 dimensions. Original work was done also by Alex Graves in 2007 in Schmidt to do multidimensional LSTMs. At the time, he applied them for images and different other tasks, but even handwriting recognition. But in 2011, just at the time he was coming to Toronto, he was doing a paper for robustness in training LSTMs. And he applied at the time the multidimensional LSTMs for timid. It was not great result, but still it counts as the first application of time frequency LSTMs for speech. So here the motivation was spectrogram reading. I'm kind of fascinated by the fact that like Jim and Victor here are like capable of like teaching, not just like reading them, but they are teaching these to their students how to read spectrogram, and I was intrigued by that. How can we do that? How can we build this capability in neural networks? And the closest thing that I was thinking about was looking at time frequency, look at the evolution. Maybe we can marginalize out all these kinds of time frequency distortions if we are learning this time and frequency. And again, this taking the convolutions to the extreme. So the work that we did before in CNNs and convolutions over frequency, we were using again fixed kernel size, fixed pooling. But here, if we have LSTMs over frequency and over time, this is the limit that we can reach. Earlier work before this one, we tried to do only frequency LSTMs, like only running LSTMs over frequency bands, and then concatenate all these features, feed it to a time LSTM. It was good, but it was not amazing. This work, we started from the very beginning on the Mel frequency spectral coefficients to work with time and frequency LSTMs. And this work has tiny little engineering differences between the multidimensional LSTM and later grid LSTM that was done actually around the same time. So earlier version of this work was submitted for publication and the same day that the grid LSTM was put in archive. So there are tiny little technical differences, but in principle, all the three models are the same. With little computational difference or adding some stability over other models. But this one was the most stable one. In this model, we are running 2 LSTMs, one over frequency and one over time, but with one memory vector, not 2 memory vectors. So it's only single memory vector that we are using. And because I was this is joint work with Genuinely from our production group at Microsoft, and we wanted to just add the smallest possible difference that will have the biggest impact. And for that work, and this was work amazing. So we did actually one layer of this feature to normalize for these features in the input, and then feeding it to the multiple layers of time of LSTMs over time. And what we kind of we're looking to see is that these that time frequency LSTMs will have this better understanding of how to features in a way that's robust to mismatch conditions between train and test. So to give some little details about the model, for the hidden units, we have only 24 hidden cells, just 24 per location. And we are running them along frequency and time. And in the second layer, we concatenate all these 24s over all positions to feed to the multiple layers of LSTMs. We, as I mentioned, we are using one memory vector, not 2. Like in grid LSTMs, you have 2. Here we have only one that's passing the memory across frequency. And we train that on 400 hours of cell phone data. The results on matched train and test conditions were not yeah.
Doesn't it introduce a lot of sequential computation which slows things down on GPUs?
So,
sorry, just right over there.
This is a very good point. For LSTMs, they have this problem that they are sequential. This is a problem to solve in training time. Yeah. And we found multiple ways of going around that. Like what Brian said, you would chunk our data in some way so that we can parallel, actually the parallelization is happening over the many batch size, not over the time X, and like there is like tons of tricks. And this is what like we had in the other paper that I mentioned. I'm just like talking about the results, but there is other tricks that we did to get this faster. Here in production setups, keeping one frame at a time, they can still keep up with. They can still work with that.
Less in frequency.
Plus in frequency, but because what we are doing in frequency is very small, and it's only 22 steps over frequency that we are executing, it turned out to be like very minimal. So for matching, here I'm comparing like multiple models. Like one of them is like normal feed-forward DNN, a 4-layer time LSTM, like LSTM over time. And I'm saying like these are the best performing systems. I'm just like picking these best numbers from the paper. We have a frequency LSTM just running over frequency, only frequency, and then feeding things to these features to multiple layers of time LSTM, or the time frequency LSTM from the very beginning, then feeding this feature to the 4-layer of LSTM. We see that the gains are consistent, but it's not significant. Like it's not huge. So it's about like 3% relative improvement. But what exactly got our attention, and that was very interesting, was that when we train on this cell phone data, and then test later on Aurora 4 test set, which is completely mismatched test set. We just got the best model that we have here, and like for time frequency LSTM, and the best model that we got there, and we test them on the 4 test conditions. We found dramatic improvement, like compared to what we were expecting, from 10 to 13% relative improvement by doing this simple feature extraction that's resilient to distortions. Was like super important. And again, this is relating to what kind of representations that we need to use. And if we are going to learn the representation, we might find out that some of these representations are resilient to noise versus others. And to see that, we needed to go to the mismatched condition. We didn't see that for matched train and test conditions. So kind of bring my talk to the end, and here I want just to brainstorm about what's still missing. And I believe it's conversational intelligence, and I'm returning back to my all-time reference, which is the Minds meeting report in 2007. So it was set of reports that got I think by NSF encouraged lots of researcher for speech headed by Janet Baker and like Jim leading like lots of like prominent researchers in the speech community to sit down together, and I think in 2005 to over two workshops to think about and brainstorm what's still missing in speech. I think they had MIND stands for like many things, like speech was the S, data mining, natural language processing. I forgot what was the L, and then M was machine translation. So there's like many areas that lots of researchers sat together and wrote these multiple reports. And this was like my all-time reference that I was like, when I was starting my PhD, there was like in Interspeech 2007, Janet would just like give this little talk about the results of the Minds meeting, and right away I went and brought the report and started kind of using it as my everyday reference. That okay, like what's the next paper to work on? Like what's the next challenge? And still there are many challenges that I'm quoting from the report that still unmet. So one of them, and again I'm rephrasing and thinking about, is to extend the notion of end-to-end speech recognition. So currently, lots of labs and like there is amazing work happening in Google by like Navdeep and Oriol and Quackley. Lots of other researchers also in Montreal and many groups working on like end-to-end speech recognition. But they are focusing more on end-to-end from the model point of view. It's end-to-end neural model. What I believe we need to do is to extend this notion to end-to-end in the application or the task. So if we are thinking end-to-end from the task point of view, go from signal to understanding, this would lead to different kind of representations that we are going to learn from data, which will it might or might not be the same as the ones that we are currently using when we have word error rates as our metric. And of course, now we need to have another metric that is focusing on understanding, not necessarily on the what, but on conveying the message. And I believe that we are going there because because of all these, systems like Siri, Cortana, Alexa is everywhere now. So industrial labs are going there anyway. Another thing that we still miss is like far field speech recognition, like reverberation, different external noise sources, you name it, and mismatched test conditions. We just scratched the surface of that, but we're not yet at the human level ability of being resilient to different test conditions. And the most important direction is the lifelong learning. How can we acquire new vocabulary? The same point that was mentioned here. How can we acquire dialects? Like, I'm like, can I increase my inventory of dialects, non-native accents as I go, as an agent? About myself as Cortana or Siri or Alexa. So like, how can I learn from user feedback? And this is one of my superheroes at Microsoft Research, like Patrice Simard. He is actually dedicating the last few years of his research and his group is to what he's calling machine teaching. How can we feedback from users to improve the system as we go? Of course, lots of work now in reinforcement learning can also help a lot in this area. And I believe this is a wide open area for research. So thank you.